Polynomials are great, but not all functions and not all applications deal with polynomial functions. In this video, we'll look at how to differentiate functions which are written in terms of quotients and products. Let's just say we knew a relationship between stress, given by S, on a tube and the outer tube diameter, d, given tension T and inner diameter, little d. The function that we've got here is the division of 16 dt and pi times d to the 4 minus little d to the 4. We don't actually know how to differentiate this kind of function yet, so we can't figure out how stress changes with tube diameter. In a previous video we looked at how to differentiate constants, powers, and sums and multiples, but essentially that just let us differentiate polynomials, not this kind of function, where we've written our function as a quotient of two functions. So using this problem as motivation, we're now going to look at rules for functions that are products or quotients and how to differentiate them. Such functions can be differentiated using the product rule or the quotient rule, depending on whether you've got a product or a quotient. And those two rules are given right here. Now both of these can actually be derived using the definition of the derivative. We're not going to do that here, but it's good to know that it can be done. The product rule says that if we have a function f of x that is itself the product of two simpler functions, u and v, then the derivative of f of x, or uv dashed, is the second function multiplied by the derivative of the first, plus the first function multiplied by the derivative of the second. This one here is called the product rule. The quotient rule looks very similar, but it is slightly different. Again, given a function f, written in terms of u and v, where u is the top function and v is the bottom function, the derivative of that quotient is given by v times u dash, take away u times v dash, and this time divided by v squared. So the big difference there is that the plus of the product rule becomes a minus of the quotient rule. And we must remember in the quotient rule to write things in the correct order. Let's look at a couple of examples. In A, we're asked to find the derivative with respect to x of the function x squared plus 4 multiplied by x minus 3x squared. Well, this is a product of two functions. The first function, x squared plus 4, and the second function, x minus 3x squared. The product rule tells us that the derivative of u times v is equal to v times u dash plus u times v dashed. So we need to identify what u and v are. I'm going to let u be the first function, x squared plus 4, and v is going to be the second. So v will be equal to x minus 3x squared. We need the derivatives of both of those to plug them into the product rule. So u dash is going to be 2 times x plus nothing. V dashed is going to be 1 take away 6x. So now we've got everything we need to plug those things back into the product rule and get the derivative of the function we're investigating. So we can write that f dash of x is going to be equal to v times u dash, or 1 minus 6x times u dash, which is 2x, plus u times v dash, or x squared plus 4, Using those results, we can now write that f dash of x is equal to v by u dash, or x minus 3x squared times 2x, plus u times v dash, so plus x squared plus 4 times v dash, which is 1 minus 6x. That's pretty much the end result, but I've got a feeling that if we multiply out all of these brackets, we might get some simplification. So have a go at that now and see if you get the same result as me. Well, I didn't really have much success, but I did end up with minus 12x cubed plus 3x squared minus 24x plus 4. So basically either of these two results is just fine. Let's have a look now at the quotient. In part B, we're asked to find the derivative with respect to x of f of x equal to x cubed on x minus 4. So the quotient rule tells us that the derivative of u on v is vu dash minus uv dash over v squared. So let's identify u and v. U is going to be x cubed, and v is going to be x minus 4. So we can write over here that u is x cubed, and its derivative then is 3x squared. V is going to be x minus 4, and its derivative is quite simply just 1. So now all we need to do is plug all of these back into our relationship for the quotient rule, and we'll get our derivative. F dash of x is equal to v by u dash, so x minus 4 by 3x squared. Remember, it's take away for the quotient rule, u times v dash, or x cubed times 1, all divided by v squared, which is x minus 4 all squared. So again, we can do a little cleaning up there. So we'll get 3x cubed minus 12x squared minus x cubed all over x minus 4 all squared. There's just a little cancellation to finish that off. We get 2x cubed. That should actually be a square. Minus 12x squared. Well, actually, let's clean that up even further by doing a little factoring. So we're going to have 2x squared outside of x minus 6 all over x minus 4 all squared. And that's our quotient rule example. So what about back to our motivating example about the hollow tube? We had the stress, capital S, on the tube being given by this relationship, S equal to 16 dt over pi times capital D to the 4 minus little d to the 4. And noting that t is a constant, and so is the inner diameter, little d. So basically here we've got a function s of capital D. Single variable function, everything's fine. We can now differentiate that because we know how to differentiate quotients, or fractions like this one. So what is the instantaneous rate of change of stress with respect to the outer diameter? Rate of change of stress, S, with respect to outer diameter, capital D, it's just going to be S dash of D, or d capital S dd, if you like. I'll probably go with this one because it looks a bit weird having dd like that. So pause the video for a moment and try to have a go at this one yourself using the quotient rule. So we're going to use the quotient rule, u on v dash, it's a bit of a mistake there, u on v, it's going to be given by vu dash minus uv dash over v squared. I'm going to let u be 16 dt and v be d to the 4 minus little d to the 4. And remember, little d and big T are just constants, and we'll treat them that way when we're finding the derivatives. So u dash is going to be 16 dt, differentiating that we're just going to get 16t. V dash, we'll just get 3 capital D to the 4. 4 capital D to the 3. So we've got everything we need to plug into the quotient rule. So S dash of D is going to be V times U dash, so that's D to the 4 minus little d to the 4, times U dash, which is 16t. Take away U times V dash, so that's 16 dt, times V dash, which is 4d to the 3, all divided by v squared. So that's d to the 4 minus little d to the 4 all squared. Now again, we can clean this up a bit, so have a go at that for yourself. So I've done a little bit of expanding and then grouped up the top part there and end up with minus 16t d to the 4 plus 3 capital D to the 4 all over capital D to the 4 minus little d to the 4 all squared. So that gives us our relationship for, as we were asked, the instantaneous rate of change of stress with respect to the outer diameter. So if we knew the values for t and little d, we could figure out that instantaneous rate of change for any diameter that we liked using this relationship. So to summarize, we now know from a previous video how to differentiate polynomials, and from this video how to differentiate products of functions and quotients of functions. So we can find, using calculus, how quantities vary with respect to each other when they can be written as sums, products, quotients, and powers of variables, or any combination of those given by a constant multiple or a sum or difference. And that's it for this video. In another video we're going to be looking at how to differentiate functions of functions, and also look at some other different functions that we haven't looked at yet, like the trig functions and exponentials.